Welcome to a review of 13.1. How many of you didn't get your exams back? I have your exam and yours, and you have to wait. I don't have it with me. I have it in my office. If you have questions about the score, why don't you go ahead and email me right after class. Chapter 13 is a very physical chapter. It has a lot to do with mechanical engineering, fluid mechanics, physics, electricity. You're going to see things, weird things like work. You've already seen work. Do you remember the definition? So we define the work as a path integral along a regular curve. And by regular curve, I'm sorry if I'm repeating myself, but this is part of the deal. R is the position vector in R3. That is class C1. That means differentiable and derivatives are continuous. Plus, you are not allowed to stop. So no matter how drunk the bug has to keep flying, and not even for a fraction of a second is he or she allowed to have velocity zero. At no point are you going to have velocity zero. And that's the position vector. And then you have some force field acting on you, no, acting on the particle at every moment. So you have an F that is acting at the location x, y. Maybe if you are in space, let's talk about x, y, z, where x is a function of t, y is a function of t, z is a function of t, which is the same as saying that r of t, which is the given position vector, is x of t, y of t. Let me put angular bracket, although I hate them because you like angular brackets for vectors. F is also a nice function. How nice? We discussed a little bit last time. It really doesn't have to be continuous. The book assumes it continuous. It has to be integrable. So maybe it could be piecewise continuous. So I say nice enough. I say continuous, piecewise. And we define the work as being the path integral over C. I keep repeating because that's going to be on the final as well. So all the notions that are important should be given enough attention in this class. So do you guys remember how we denoted F? F was in general three components in R3, F1, F2, F3. They are functions of the position vector, well, the position x, y, z. And the position is a function of time. So all in all, after you do all the work, keep in mind that when you multiply with the dot product, the integrand will give you what? A time integral? From a time t0 to a time t1, you are here at time t0 and you are here at time t1. Maybe your curve is piecewise differentiable. You don't know what it is, but let's assume just a very nice smooth arc here. Of what? Of f1 times, what is that? X prime of t plus f2 times y prime of t plus f3 times z prime of t dt. So keep in mind that Mr. dr is your friend, and he was, what was he? He was defined as the velocity vector multiplied by the infinitesimal element dt. Say it again, the velocity vector R prime was a vector in R3 multiplied by the infinitesimal element dt. So we reduced this Calc 3 notion, path integral, to a Calc 1 notion, which was a simple integral from t0 to t1, and we've done a lot of applications. What else have we done? We've done some integral of this type. over another curve, script C. I'm repeating also for Alex a little bit, although you caught in the process, and there are 2 or 3 people who need an update. Maybe I have another function, g and ds, and this is an integral that in the end will depend on s, but s itself depends on t. So if I were to re-express this in terms of t, how would I re-express the whole thing? G of s of t, whatever that is, and Mr. ds was what?
S prime of t dt.
Right, so this was that s prime of t was the speed of the arc of a curve. So you have an r of t and r3, a vector, and the speed was, by definition, the arc length element was by definition integral from t0 to t of the speed r prime in magnitude d tau. So let me put tau because I'm Greek. And it's all Greek to me. So the tau, some people call the tau the dummy variable. I don't like to call it dummy. It's a very smart variable, tau. It goes from t0 to t. So what you have is a function of t. This guy is speed. So when you do that, here ds becomes speed r prime of t times dt. This was your old friend ds. And let me put on top of this guy, put speed, because he was so important to you. You cannot forget about him. So that was reviewing 13.1 and 13.2. There were some things in 13.3 that I pointed out to you are important. 13.3 was independence of path. Let it write magic, no. Magic section, no. It have to be serious. So let's independence of path of certain type of integrals, of some integrals. And an integral like that, a path integral, is independent of path when? When would such an animal, look at this pink animal beside, when would this not depend on the path you are taking between 2 given points? So I can move on another arc and another arc and another regular arc and all sorts of regular arcs. It doesn't matter which path I'm taking.
If that force is conservative.
If the force is conservative, excellent, Alex. And what did it mean for a force to be conservative? How many of you know? It's no shame, just raise hands. If you forgot what it is, don't raise your hand. But if you remember what it means for a force F, force field, may the force be with you, be conservative, then what do you do? Say F is conservative by definition. When, if and only if, there is a so-called potential, scalar potential, thank you, Bekzat, a scalar potential function F instead of there is. I didn't want to put this because a few people told me they got scared about this symbolistic set. This means there exists. Okay? Smooth potential such that, at least it's differentiable C1, such that the nabla of F, what the heck is that? The gradient of this little f will be the given f. And we saw all sorts of wizards here, like Harry Potter, Nitishmita, Bekzad, well, there are many, Alex, Aaron, many, Matthew. So what did they do? They guessed the scalar potential. I'm gonna stop because there are 10 of them. It's a whole school of Harry Potter. How did they find the little f? through witchcraft. No. Normally you
I
should.
actually found it through witchcraft. Tell you that?
You did.
Yeah,
I think you can do it through witchcraft. But practically everybody has the ability to guess. Why do we have the ability to guess and check? Because our brain does the integration for you. Whether you tell your brain to stop or not, when your brain, for example, sees this kind of function, and now I'm gonna test your magic skills on a little harder one. I didn't want to do an R2 valued vector function. Let me go to R3. But I know that you have your witchcraft handy, so let's say somebody gave you a force field that is x, y, z, I plus x, z, j plus x, y, k, and you're gonna jump and say this is a piece of cake. I can see the scalar potential. I just wave my magic wand and I'm gonna get it. Oh my God, yes guys, you saw it fast. Okay, I should be proud of you, and I am proud of you. I've had many classes where the students couldn't see any of the scalar potentials that I gave them, that I asked them to guess. How did you do it? Did you integrate this with respect to it? In the back of your mind you did, and then you guessed one, and then you said, okay, so it should be x, y, z. Does it verify my other two conditions? And you say, oh yeah, it does, because if I prime with respect to y, I have exactly x, z. If I prime with respect to z, I have exactly x, y, so I got it. And even if somebody said x, y, z plus 7, they would still be right. In the end, you can have any x, y, z plus a constant. In general, it's not so easy to guess, but there are lots of examples of conservative forces where you simply cannot see the scalar potential or cannot deduce it like in a few seconds. Okay? Expect something easy though, like that, something that you can see. Let's see an example. Assume this is your force field acting on a particle that's moving on a curve in space, and it's stubborn, and it decides to move on a helix because it's a, I don't know what kind of particle would move on a helix, but suppose it's not a particle, it's just a little train or a drunken bug or something, and you are moving on a helix. Now, suppose that helix will be r of t equals cosine t, sine t, and t, where you have t at 0 to start with. What do I have at 0? The point 1, 0, 0. That's the point. Let's call it A. And let's call this B. I don't know what I want to do. I'll just do complete rotation just to make my life easier. And this is B. And that will be A at t equals 0 and B equals 2 pi. So what will this be at B?
1, 0, 2 pi.
1, 0, and 2 pi. So you perform a complete rotation and come back. Now, if your force is conservative, you're lucky because you know the theorem that says, in that case, the work integral will be independent of path, and due to the theorem in what section was that again? 13.3, independence of path, you know that this is going to be, let me rewrite it one more time as with gradient of f instead of big F. And this will become what? F of the q, not the q, in the book is f of q minus f of q, f of b minus f of a, right? What does this mean? You have to measure to evaluate the coordinates of this function xyz, where t equals 2 pi minus xyz, where t equals what? 0. And now I have to be careful because I have to evaluate them. So when t is 0, I have x is 1, y is 0, and t is 0. And in the end, it doesn't matter, I can get 0. I mean, get 0 for this and get 0 for that as well. So when this is 2 pi, I get x equals 1, y equals 0, and t equals 2 pi. So in the end, both products are 0, and I got a 0. So although the drunken bug works very hard, works hard in our perception to get from a point to another, the work is 0. Why? Because it's a vector value thing inside, and there are some annihilations going on. All right, so that reminds me of another example. So we are done with this example. Let's go back to our washer. I was just doing laundry last night, and I was thinking of the washer example, and I thought of a small variation of the washer example, just assuming that I would give you a pop quiz. I'm not giving you a pop quiz right now, but if I gave you a pop quiz now, I would ask you example 2, the washer is performing a circular motion, and I want to know the work performed by the centrifugal force between various points. So have this circular motion, the centrifugal force. This is the centripetal, I'm sorry. I'll take the centrifugal force. And that was last time we discussed that. That was extending the radius, the initial, the vector value position. So you have that at every point, xi plus yj. And you want f to be also xi plus yj, but it points out outside from the point on the circular trajectory. And I asked you, find W performed by F in one full rotation. We gave the equation of motion being cosine p y sine t, if you remember from last time. And then W2, let's say, is performed by F from t equals 0 to t equals pi. I want that as well. And W2 performed by F from t, that means t0 to t equals 0 to t equals pi over 4. These are all very easy questions, and you should be able to answer them in no time. Now, let me tell you something. If we are in plane, not in space, but it doesn't matter. It's like the third coordinate would be 0, piece of cake. Your eye should be so well trained that when you look at the force field like that and people talk about work, you should ask yourself, is it conservative? And it is conservative. And that means little f is what? Mitish said that yesterday. Why did you go there? You want to sleep today? I'm just teasing you. I got so comfortable with you sitting in the front row.
So I took his spot.
She's telling me
Oh.
I'm not used to sitting here.
It's okay, it's fine. I still give him credit for what he said last time. So, do you guys remember he gave us this answer, x squared plus y squared over 2, and he found the scalar potential through witchcraft in about a second and a half? Okay, we are gonna conclude something. Do you remember that I found the answer by a funny explanation? I got W to be 0. But if I were to find another explanation why the work would be 0 in this case, it would have been 0 anyway for any force field, even if I took the F to be something else. So assume that F would be G. Really wild, crazy, but still differentiable vector value function. G differential. Would the work W1 be the same for G? Why?
Displacement 0.
Since it's conservative, you have a closed loop, right? So the closed loop will say, take F at the terminal point minus take F at the initial point. But if it's a loop motion, your terminal point is the initial point. Duh. So you have the same point, the P and E. B equals Q if it's a closed curve. So for a closed curve, we also call that a loop. I could have asked you, but it would have been too easy and you would have gotten $1 for free like that. So any closed curve is called a loop. If your force field is conservative, attention, you might have examples like that in exams, then it doesn't matter who little f is. If P equals Q, you get 0 anyway. But the reason why I said you would get 0 on the example F last time was a slightly different one. What does the engineer say to himself?
Force is perpendicular.
Very good. Whenever the force is perpendicular to the trajectory, I'm going to get 0 for the force, because at every moment, the dot product between the force and the displacement direction, which would be like dr, the tangent to the displacement, would be 90, and cosine of 90 is 0. So that's another reason. Reason of last time was F perpendicular to the R prime direction. R prime being the velocity vector. Look, when I'm moving in a circle, this is the force. And I'm moving, this is my velocity, is the tangent to the circle, and the velocity and the normal are always perpendicular at every point. And that's why I have 0. So note that even if I didn't take a closed loop, what would the answer be from 0 to pi? Still 0 because of that. 0. How about from 0 to pi over 4? Still 0. Still 0. And of course, if somebody would not believe them, if somebody would not understand the theory, they would do the work and they would get to the answer and say, oh my God, yeah, I got 0. All right? Okay. Now, what if somebody, and I'm going to spray this. Can I go ahead and erase the board and move on to example 3 or whatever? Yes? Okay. All right.
Could we see a non-conservative force?
Yeah, that's what exactly. You are a mind reader. You are going to guess my mind. And I'm going to pick a nasty one. And since I'm doing review anyway, you may have one like that in the exam. You may have both, one that involves a conservative force field and one that does not involve a conservative force field. And we can ask you, find us the work along 2 different paths. And I've done this type of example before. Let's take f of x and y in plane. In R2, I take xyi plus x squared y j. And the problem would involve my favorite picture. Y equals x squared and y equals x are 2 paths. One is the straight path, one is the parabolic path. They go from 0, 0 to 1, 1 anyway. And I'm asking you to find W1 along path 1 and W2 along path 2. And of course, example 3, if this were conservative, you would say, it doesn't matter what path I'm taking, I'm still getting the same answer. But is this conservative?
No. Because you
No.
said it wasn't.
Very good. So how do you know? That's one test when you are in R2. There is the magic test that says, this is, let's say this is M and let's say this is N. You would have to check if M sub Y, very good, I'm proud of you. You're ready for 3350, by the way, is equal to N sub X. M sub Y is X. N sub X is 2XY. They are not equal. So that's me crying that I have to do the work twice and probably I'll get two different examples. Is there, if you read the book, I'm afraid to ask how many of you opened the book at section 13.2, 13.3, but did you read any of them?
It is, you read it.
Oh, good, exactly. There is another criterion for a force to be conservative. If you are not to eat piece of cake, you do that, right? Yes, sir.
Good, I have to check this out.
The curl criterion, excellent. The curl has to be 0. So if F in R3 is conservative, then you get if and only curl F is 0. Now let's check what the heck was curl. You see, mathematics is not a bunch of disjoint discussions like other sciences. In mathematics, if you don't know a section or you skipped it, you were sick, you had a date that day, you didn't study, then it's all over because you cannot understand how to work out the problems and materials if you skip the section. Curl was the one where we learned that we use the determinant. That's the easiest way. I came with a t-shirt, but that t-shirt really doesn't help because it's easier to, instead of memorizing the formula, to set up the determinant. So you have the operator, derivative with respect to x, y, z, followed by what? F1, F2, F3. Now in your case, I'm asking you if you did it for this F, what is the third component? 0. So this guy is 0, this guy is x squared y, and this guy is xy, and it should be a piece of cake, but I want to do it one more time. I times the minor derivative of 0 with respect to y is 0, minus derivative of x squared y with respect to z, 0. Okay, alrighty. Plus j minus j because I'm alternating. You've known enough linear algebra to know I'm expanding along the first row. I have a minus. Alright. ddx of 0, 0. Derivative of xy with respect to z, 0. Plus k times the minor corresponding to k, derivative to xy. The derivative.
Yeah, this isn't n equals 0.
Oh yeah, that's the one where it's not because that's not it's not conservative, different from 0. So what do you get? You get 2xy minus x, right? But I don't know how to write it better than that. It doesn't matter, leave it like that. So this would be 0 if and only if x would be 0, but otherwise the discount or y was 1/2. But in general, it's non-zero. Good. So f is not conservative. And then we can say goodbye to the whole thing here and move on to computing the works. What is the only way we can do that? By parameterizing the first path. But I didn't say which one is the first path. This is the first path. So x of t equals t, y of t equals t is your parametrization, the simplest one, and then w1 will be integral of, I'm too lazy to write down x of t, y of t, but this is what it is, times x prime of t plus x squared y times y prime of t dt, where
Isn't that just x, y, dx, y prime, or y, what, 2y?
this is
S of x
f1,
dx.
this is f2, this is x prime and this is y prime, because this thing is just f dot dr, right?
Right, but what I'm asking, is that not the same as just f1 dx? Because we're going to do a chain rule anyway.
If I put dx, I cannot put this. Okay, this times that is dx. This guy times
you
this
can't
guy
use
is
your-
dx.
then you can't
Then
use
I
your
cannot use the t's.
All right, there we go.
Okay. All right. So I have integral from 0 to 1 tt times 1 t squared. If I make a mistake, that would be silly algebra mistake. Please shout. All right, plus t cubed times 1 dt. How much is this? T cubed over 3 plus t to the 4th over 4.
It's just 2, or no. 7/12.
Very good. Do not expect that we kill you with computations on the exams, because that's not what we want. We want to test if you have the basic understanding of what this is all about. Not to kill you with, okay, I'm not going to say that in front of the cameras, but everybody knows that. There are professors who like to kill you with computations. Now, we live in a different world. If I give you a long polynomial sausage here, and I ask you to work with it, that doesn't mean that I'm smart. Because MATLAB can do it, Mathematica, you get some very nice simplifications over there. So I'm just trying to see if, rather than being able to compute with no error, you are having the basic understanding of the concept. And the rest can be done by the mathematical software, which nowadays most mathematicians are using. I mean, if you ask me 15 years ago, I think I knew colleagues at all the ranks in academia who would not touch Mathematica or MATLAB or Maple, saying that's that tool from Evo or something. But now everybody uses. Engineers use mostly MATLAB, as I told you. Mathematicians use both MATLAB and Mathematica. Some of them use Maple, especially the ones who have demos for K-12 level teachers. But MATLAB is a wonderful tool, very powerful in many ways. If you're doing any kind of linear algebra project, as 3 or 4 of you are taking linear algebra, you can always rely on MATLAB being the best of all of the above. Okay, W2. For W2, I have a parabola, and it's again a piece of cake. X prime will be 1, y prime will be 2t. When I write down the whole thing, I have to pay a little bit of attention when I substitute, especially when I'm taking an exam under pressure. Okay. X squared is t squared, y is t squared, times y prime, which is 2t. So are you guys with me? This is x prime, this is y prime. Let me change colors. This is, all politicians change colors, but I'm not a politician, but I'm thinking it's useful for you to see who everybody was. This is the F1 in terms of t. That's the idea of what that is. And this is F2 in terms of t as well. Am I got another answer? Absolutely. I'm gonna get another answer. Is it obvious to everybody? I'm gonna get another answer. Yeah. So I don't have to put the t's here, but I thought it was sort of neat to see that t goes from 0 to 1. And what do I get? This whole animal is t cubed plus 2t to the 5th. So when I do the integration, I get t to the 4 over 4 plus, shut up Magdalena, tell people what. Very good. With yeah, so you have, he's done the simplification.
You get the same values. Plug in 1, you get 7/12 again.
So I'm asking you, what is it? So 0, 1. So I'm asking you, why do you think we get the same value? Because the force is not conservative, and I went on another path. I went on one path, and I went on another path, and look, obviously my expression was different. It's like one of those math games or UIL games. Look at the algebra. The polynomials are different. What was my luck here? I took 1.
Yeah.
I could have taken 2. So instead of 1, I would have taken another number. Then the higher the power, the bigger the number would have been. I could have taken
You could have taken -1 and you still would have got the same answer.
Yeah, there are many reasons why that is. But anyway, note that when you take 1, 1 to every power is 1. And yeah, and you were lucky, but in general, keep in mind that if the force is conservative, in general, in most examples, you're not going to get the same answer for the work because it does depend on the path you are taking. I think I have reviewed quite everything that I wanted. So I should be ready to move forward. So I'm saying we are done with sections 13.1, 13.2, and 13.3, which was my favorite, because it's not just the independence of path that I like, but it's the so-called fundamental theorem of calculus 3, which says fundamental theorem of the path integral, saying that you have f of the endpoint minus f of the origin, where little f is that scalar potential, assuming your function was conservative. I'm going to call it the fundamental theorem of path integral. Last time I told you the fundamental theorem of calculus is Federal Trade Commission. We refer to that in Calc 1. But this one is the fundamental theorem of path integral. Remember it, because at least one problem out of 15 or something on the final, I don't know, it's going to be many, is going to ask you to know that result. This is an important theorem. And another important theorem that is starting right now is Green's theorem. Green's theorem is a magic result. I have a t-shirt with it. I didn't bring it today. Maybe I'm going to bring it next time. First, I want you to see the result. And then I'll bring the t-shirt to the exam. So, okay. All right. Assume that you have a so-called Jordan curve. You see, mathematicians don't call mathematical objects by their names. We are crazy people, but we don't have a big ego. We would not say a theorem of myself or whatever. We never give our names to that. But all through calculus, you saw all sorts of results. Like you see, the Jordan curve is a terminology, but then you see everywhere the Leibniz rule. Did Leibniz care to call it his own rule? No. But Euler's number, or these are things that were discovered, and in honor of that particular mathematician, we call them names. We call them the name of the mathematician. Out of curiosity, for 0.5 extra credit points, find out who Jordan was. Jordan curve is a closed curve that in general could be piecewise continuous. So you have a closed loop over here. So in general I could have something like that does not enclose, that encloses a domain without holes. Holes or punctures are the same thing.
So doesn't it need to be continuous?
No, I said it is.
You said piecewise.
Piecewise. This is piecewise.
Oh, so it's piecewise. Okay.
So you have a bunch of arcs, finitely many, let's say in your case, and finitely many arcs. They have corners, but you can still define the integral along such a path. What? Oh, and also for another 0.5 extra credit, find out who Mr. Green was, because he has several theorems. There are, through mathematics and fluid mechanics and variational calculus, there are several identities that are called Green's. There is this famous Green's theorem, but there are Green's first identity, Green's second identity, and all sorts of things. And find out who Mr. Green was, and as a total you have 1 point extra credit. And you can turn in that regular essay, like a 2-page thing you want, biography of these mathematicians, if you want. Just a few paragraphs. So what does Green's theorem do? Green's theorem is a remarkable result which links the path integral to the double integral. It's a remarkable and famous result. That links the path integral to on a closed curve to a double integral, not to a double integral over the domain enclosed. I can say the domain inside, but you have to understand it's enclosed by the curve. Okay? All right, and assume that you have M and N are C1 functions of x and y. What does it mean? M is a function of xy, N is a function of xy in plane. Both of them are differentiable with continuous derivative. They are differentiable. You can take the partial derivatives, and all the partial derivatives are continuous. That's what we mean by being C1 functions. And there the magic happens. So let me show you where the magic happens. This in the box. The path integral over C of m dx plus n dy is equal to the double integral over the domain enclosed. Okay, this is the C. On the boundary, you go counterclockwise, like any respectable mathematician would go in the trigonometric sense, which is counterclockwise. And this is the domain D enclosed by C. And you put here the integral, which is magic. You have, this is easy to remember for you. This is not easy to remember unless I take the t-shirt to the exam and you cheat by looking at my t-shirt. No, by the time of the exam, I promised you you're gonna have at least 1 week, 7 days or more, 10-day period in which we will study samples, various samples of old finals. I'm gonna go ahead and send you some by email. Do you mind? Okay. In the next week, after this week, we are gonna start reviewing. And by dA, I mean dx dy, the usual area element in Cartesian coordinates, the way you are used to it the most. And then Alex is looking at it and says, well, didn't I tell her that the most elegant way is to put it with dx dy? This is what we call a one form in mathematics. What is a one form? It's a linear combination of these infinitesimal elements dx dy in plane with some scalar functions of x and y in front of them. Okay, so what do? We integrate a one form. The book doesn't talk about one forms because the book is actually written for the average student, the average freshman or the average sophomore. But I think we have enough exposure to the notion of one form so I can be a little bit more elegant and more rigorous in my speech. If you were a graduate student, you most likely would know this is a one form. That's actually the definition of a one form. And you say, what is this? This is actually two form, but you are going to say, wait a minute, I have a scalar function, whatever that is, from the integration, right? In front of a dx dy, but they never said that dx dy is a two form. Actually, I did, and I didn't call it a two form. Do you remember that I introduced to you some magic wedge product? And we said this is a tiny displacement, dx infinitesimally small. Imagine how much the video will see. There is an infinitesimal displacement dx and an infinitesimal displacement dy, and you have some sort of a signed area. So we said we don't just take dx dy, but we take a product between dx dy with a wedge, meaning that if I change the order, I'm going to have minus dy dx. This is typical exterior derivative theory. Exterior derivative theory. And it's a theory that starts more or less at the graduate level. And many people get their master's degree in math and never get to see it, and I pity them, but this is life. On the other hand, when you have dx wedge dx, the area between dx and dx is 0, so I'm very happy I get rid of those. When I have the sign area between the displacement dy and itself is 0. So these are the basic properties that we studied about the sign area. I want to show you what happens. I'm going to pull, I'm going to erase here. I'm going to show you later. I'm going to prove this theorem to you later using these tricks that I just showed here. I will provide a proof. To this formula. Okay, and let's take a look at that, and we say, well, can I memorize that by the time of the final? Yes, you can. What is beautiful about this, it can actually help you solve problems that you didn't think would be possible. For example, example 1, and I say that would be one of the most basic ones. Find the geometric meaning of integral over C, where C is a closed loop. Okay, C is a loop, piecewise defined Jordan curve, and I integrate out of something weird, and you say, oh my God, look at her. She picked some weird function where the part in front of dx is m, and the part in front of dy is n, the m and n functions. Why would she pick like that? You wouldn't know yet, but if you apply Green's theorem, assuming you believe it's true, you have double integral over the domain enclosed by this loop. The loop is enclosing this domain. Of what? Now, shut up, and I want you to talk. What am I going to write over here? 1 plus 1. How funny is that? 1 minus 1. 1 plus 1 equals 2, last time I checked. And this is dA. And what do you think this animal would be? The constant 2 always can escape in front, so we don't want it. Just kick it up. What is that remaining double integral over d of dA? You have seen this guy all through the Calculus 3 course. You tired of it. You said, cannot wait for this semester to be over because this is the double integral of 1 dA over d. What in the world is that? That is the area. Very good. This is the area of the domain D inside the curve. The shaded area is this. So you have discovered something beautiful, that the area of the domain enclosed by a Jordan curve equals 1/2, because you pull the 2 out in front here, it's going to be 1/2 of the path integrals over the boundary. This is called boundary of the domain. C is the boundary of the domain. Some mathematicians, I don't know how far you want to go with your education, but in a few years you might become graduate students, and even some engineers use this notation, boundary of D, del D. That means the boundary, the frontier of a domain, the fence of a range. That is del D, but don't tell the rancher because he will take his gun out and shoot you, thinking that you are off the hook or you're after something weird. Right? So that's the boundary of the domain. And then you have minus y dx plus x dy. We discovered something beautiful, something important. And now I'm asking, with this exercise 1, which I could even call a lemma. A lemma is not quite a theorem because it could be based on a theorem. It's a little result that can be proved in just a few lines without being something sophisticated, based on something you knew from before. Okay, so this is called a lemma. When you have a sophisticated area to compute, or even can you prove, if you believe in Green's theorem, can you prove that the area inside the circle is pi r squared? Can you prove that the area inside of an ellipse is, I don't know what? Do you know the area inside of an ellipse? Nobody taught me in school. I don't know why. It's so beautiful. I learned what an ellipse was in 11th grade in high school, and again, a review as a freshman, analytic geometry. So we've seen conics again, we've seen
conics in 10th grade.
Ellipses,
Might have seen it.
hyperbola.
That was-
But nobody told me, like, give you an ellipse, compute the area inside. I had no idea. And I didn't know the formula until I became an assistant professor. I was already in my 30s. That's a shame to see that thing for the first time. Okay, so let's see if we believe this lemma and the Green's theorem, of course, but let's apply the lemma primarily from the Green's theorem. Can we actually prove that the area of the disk is pi r squared and the area of the ellipse inside the ellipse will be God knows what? And we will discover that by ourselves. I think that's the beauty of mathematics, because every now and then, even if you discover things that people have known for hundreds of years, it still gives you the satisfaction that you did something by yourself, all on yourself. Like when you build a cupboard, when you build a table. There are many more beautiful tables that were built before you, but still it's a lot of satisfaction that you do all by yourself. It's the same with mathematics. So let's see what we can do now for the first time. Not for the first time, we did it in other ways. Can you prove using the lemma or Gauss theorem, which is the same thing, either one, that the area of the disk of radius r, this is dr, the disk of radius r is pi r squared. I hope so, and the answer is, I hope so, and that's all. Area of the disk of radius r. Oh my God. So you go, well, if I knew the parametrization of that boundary C, it would be a piece of cake, because I would just, I know how to do a path integral now. I've learned in the previous sections, and it should be easy. Can we do that? So let's see. Without computing the double integral, because I can always do that with polar coordinates, and we are going to do that. Let's do that as well as practice, as silly review for the exam. But another way to do it would be what? 1/2 integral over the circle. And how do I parameterize a circle of fixed radius r? Who tells me? X of t will be, that was chapter 10. Everything is a circle in mathematics.
R cosine t.
R cosine t, excellent. Y of t is r sine t. So finally, I'm going to go ahead and use this one, and I'm going to say, well, minus y to be plugged in. This is minus y. Multiplied by dx. Well, you say, wait a minute, dx with respect, what is dx? Dx is just x prime dt. dy is just y prime dt, and t goes out. He's vanished. No, he's the most important guy. So t goes from something to something else. We will see that later. What is x prime dt? X prime is minus r sine t, Magdalena. Minus r sine t. That was x prime. Change the color. Give people some variation in their lives. Plus r cosine t, because this is x. Times dy, which is r cosine t. So it suddenly became beautiful. It looks, first it looks ugly, but now it became beautiful. Why? How come it became beautiful?
Because you got sine squared plus cosine squared.
Because I got a plus, if you pay attention, plus sine squared plus cosine squared. So I have, what is sine squared plus cosine squared? I heard there are students in trig, a colleague told me, who still don't know that. This is the most important thing you learn in trigonometry, is Pythagorean theorem, right? So you have 1/2 integral r, no, I'm lazy, I'm going slow, r dt, t from what to what? From 0 times 0, I'm starting wherever I want, actually. And I go counterclockwise until 2 pi.
Why is that not r squared?
Should be r squared.
I'm sorry, guys. I'm sorry. I don't know what I understood for r squared. Good. 1/2 r squared times 2 pi. So we have pi r squared, and if you did not tell me it's r squared, we wouldn't have gotten the answer. That's good. What's the other way to do it? If a problem on the final would ask you prove in 2 different ways that the area of a disk is pi r squared using Calc 3 or whatever, the double integral, right? Right?
You could have done Cartesian coordinates as well, if that counts as a second way.
Yeah, you can. Okay, what would this be? Oh my God, this would be -1 to 1 minus square root 1 minus x squared to square root 1 minus x squared. Am I right, guys?
Yep.
1 dy dx. Of course, it's a pain.
You can double that and set the bottoms both equal to 0.
Right. So we can do by symmetry.
Yeah.
Shall I erase or leave it? You understand what Alex is saying? This is twice the integral that you will get.
Just write it next to it where you're
Actually,
saying
4
equals.
times, you see, Alex, because you have
Oh, yeah.
symmetry with respect to the x-axis and symmetry with respect to y-axis. And you can take 0 to 1 and 0 to that. And you have x from 0 to 1. You have y from 0 to square root of 1 minus x squared, like the strips. And you have 4 times that A1, which would be the area of the first quadrant, and you can do that a little easier. But the best way to do that is not in Cartesian coordinates. The best way is to do it in polar coordinates. Always remember your Jacobian is r. So you have Jacobian r, erase, let's put r directly, and then dr d theta. But now you say, wait a minute, Magdalena, you said r is fixed. Yes, that's why I need to learn Greek, because it's all Greek to me. Instead of r, I put rho as a variable, and I say rho is between 0 and r. R is fixed. That's my bad luck. Big R is not usually written as a variable from 0 to some. I cannot use that. So I have to use a Greek letter, whether I like it or not. And theta is from 0 to 2 pi, and I still get the same thing. I get r rho squared over 2 between 0 and r, and I have 2 pi, and in the end that means pi r squared, and I'm done. And you say, wait, this is example 4, whatever example, this is example 4, 5. You say, this is a piece of cake. I have 2 methods showing me that the area of the disk is so, pi r squared is so trivial. Yeah, then let's move on and do the ellipse. We could have been smart and done the ellipse from the beginning, and then the circular disk would have been just a trivial particular example of the ellipse. But let's do the ellipse with this magic formula that I just taught you. In the finals, I'm going to send you a bunch of finals. You're going to be amused because you're going to look at them and you say, regardless of the year and semester, when the final was given for Calc 3, there was always one of the problems at the end using a direct application of Green's theorem. So Green's theorem is an obsession, and not only at Tech. I was looking at UT Austin, A&M, other schools, California, Berkeley, all the Calc 3 courses on the final have at least one application, direct application of applying principle. Okay. So, what did I say? I said that we have to draw an ellipse. How do we draw an ellipse without making it ugly? That's the question.
Draw a circle.
Draw a circle. Good answer. Okay. All right. And guys, it started really bad. So I'm doing what I can. I should have trying to do more coffee today because I'm very insecure and very shaky. Okay, so I have the ellipse in standard form of center O, x squared over a squared plus y squared over b squared equals 1. And now you're going to tell me who is A and who is B. What are they called? Semi-axis, A and B. Good. Find the area. I don't like, okay, let's put B inside and let's put C outside the boundary. So area of the ellipse, domain D, will be, by the lemma, 1/2 integral of over C. This is C, is not L. Don't confuse it. It's my beautiful script C. I've tried to use it many times. Gonna be minus y dx plus x dy. Again, why was that? Because we said this is M and this is N, and Green's theorem will give you double integral of n sub x minus m sub y. So you have 1 minus minus 1, which is 2. And 2 got out. Okay, that's how we proved it. Okay, problem is that I do not know the parametrization of the ellipse. And if somebody doesn't help me, I'm going to be in big trouble. And I'll start cursing, and I'm not allowed to curse in front of the classroom. But you can help me on that, because this reminds you of a famous trig identity, the fundamental trig identity. If this would be cosine squared of theta, and this would be sine squared of theta as two animals, their sum would be 1. And whenever you have sums of some squares thingies, then you have to think trig. So what would be good as a parameter? Okay, what would be good as a parametrization to make this come true?
The cosine of theta would equal x over n.
So then x would be 8 times.
The cosine of theta.
Do you like theta? You don't, because you're not Greek. That's the problem. If you were Greek, you would like it. We had a colleague who's not here anymore, Greek from Cyprus, and he claimed that the most important alphabet is the Greek one, and that's why the mathematicians adopted it. Okay, beside it. How do you check? You always think, okay, this over that is cosine, this over this is sine, square them, I get exactly that, and I get a 1. Good. I'm in good shape. I know that this implicit equation, this is an implicit equation, happens if and only if I have this system of the parametrization with t between anything I want, including the basic 0 to 2 pi interval. And then if I were to move all around for time real t, I would wind around that circle infinitely many times between time equals minus infinity, that nobody remembers, and time equals plus infinity, that nobody will ever get to know. So those are the values of all the real values, actually. I only need it from 0 to 2 pi to wind one time around, and this is the idea. I wind one time around. Now people, you're going to see mathematicians are not the craziest people. I've seen engineers and physicists use a lot this sign. Do you know what this means?
It means 1 full revolution.
It means a full revolution. You're going to have a loop. Loop starts wherever you want. Here and goes counterclockwise. And they put this little sign showing I'm going counterclockwise on a closed curve or a loop. All right. Don't think they're crazy. This was used in lots of scientific papers in math, physics, engineering, and so on. Okay. Let's do it then. Can we do it by ourselves? I think so. Let's see. 1/2 is 1/2. And I don't like the thing because it's not nice. Integral of time from 0 to 2 pi it should be measured. Y minus b sine t. Dx. Who tells me that? That's x prime. Very good. Minus a sine t. How hard is that? It's a piece of cake. Plus x. Very good. A cosine t. Times b cosine t. And dt. And this thing, look at it. It's huge. It looks huge, but it's so beautiful because AB. Why is it AB? It's AB because sine squared plus cosine squared inside becomes 1. And I have plus AB, AB out. Kick out the AB. Kick out in the A and the B. And you get something beautiful. Sine squared t plus cosine squared t is your old friend. And he says, I'm 1. Look how beautiful life is for you. Finally, we proved it. What did we prove? We are almost there. We got a half. A constant that you kick out, AB,
That's 2 pi.
times 2 pi. Good. 2 goes away. And we got a magic thing that nobody taught us in school because they were mean. They really didn't want us to learn too much. That's the thingy. AB pi. AB pi is what we were hoping for because look, I mean, it's almost too good to be true. When it's a disk, a radius R, A and B are equal, and they are the radius of the disk, and that's why we have pi r squared as a particular example of the disk of the area of the ellipse. Now, when I saw it the first time, I was like, well, I'm glad that I lived to be 30 or something to learn this, because nobody had showed it to me in K-12 or in college, and I was a complete ignorant. I was a PhD and I didn't know it. And then I said, oh, that's why I did. Yes, okay. All right. So it's so easy to understand once you learn the section. If you don't learn the section, you will not be able to understand. Okay, all right. I'm going to go ahead and erase this. And I'll show you an example that was popping up like an obsession with the numbers changed in most of the final exams that happened in the last 3 years, regardless of who wrote the exam, because this problem really matches the learning outcomes of just about any university, any good university around the world. So you'll say, wow, it's so easy. I could not believe it that how easy it is. But once you see it, you'll say, wow, it's easy. Okay. Let's try this one. You have a circle, and the circle will be a circle radius r given an original of coordinate 0, 0. And I'm going to write I'm going to give you a very simple one. Compute in the simplest possible way. If you don't want to parameterize the circle, you can always parameterize the circle, right? but you don't wanna. You wanna do it the fastest possible way without parameterizing the circle, without writing down what I'm writing down. You're in a hurry. You have 15 minutes left of your final, and you are looking at me and say, I hope I get an A in this final. So what do you have to remember when you look at that? M and N. M&M, no, M and N, okay. And you have to remember that you are over a circle, so you have a closed loop, and that's a Jordan curve that's enclosing a disk. So you have a relationship between the path integral along the C and the area integral along the D, over D, which is of what? Is m sub x minus m sub y. So let me write it in this form, which is the same thing. My students mostly prefer to write it as m sub x minus m sub y. The t-shirt I have has it written like that because it was bought from nerdytshirt.com, and it was especially created to impress nerds. And of course, if you look at the Dell notation, that gives you that kind of snobbish attitude that you are a scientist. Okay, so what is this gonna be then? Double integral over D, m sub x is a piece of cake 5, m sub y is a piece of cake 3, dx dy equals 2 out times the area of the disk, which is something you know, and I'm not going to ask you to prove that all over again. So you have to say 2, I know the area of the disk, pi r squared. And that's the answer, and you leave the room, and that's it. It's almost too easy to believe it, but it was always there in the simplest possible way. And now I'm wondering if I were to give you something hard, because as you know my theory that when you practice on something in the classroom, you have to be working on harder things in the classroom to do better in the exam. So let me cook up something ugly for you. The same kind of disk, and I'm changing the functions, and I'll make it more complicated. Let's see how you perform this one. We avoided that one probably on finals because I think the majority of students wouldn't have understood what theorem they needed to apply. It looks a little bit scary, but let's say that I'm giving you the hint. Apply Green's theorem on the same path integral, which is a circle of origin O and radius R, and I'll draw counterclockwise. You apply Green's theorem, and you say, I know how to do this because now I know the theorem. This is M, this is N. And my t-shirt did not say M and N, it said P and Q. Do you want me to put P and Q? I put P and Q, so I can have this like it is on my t-shirt. So this is gonna be P sub X, no, Q sub X, sorry, M and N. So the second one with respect to X, the one that sticks to dy is prime with respect to X. The one that sticks to dx is prime with respect to y. And I think the one time when Dr. my friend and colleague wrote that, he did it differently. He wrote something like just upward, I don't remember what, he put this one. And then the student was used to dx dy and got completely confused. So pay attention to what you were saying, because most of us write it in x and y first, and we consider the derivative with respect to x of q because that is the one next to dy. And when he gave it like that, He messed completely everybody's notations and mine. I mean, no. Good students still did it. So you guys have to put it in the standard form and pay attention to what you are doing. Right? So that one form can be swapped by people who try to play games and confuse you. Now, just to play a game. Now on this one, so you have q sub x minus p sub y, you have 3x squared minus minus, so you have plus 3y squared. Good. Wonderful. Am I happy? You think I'm happy? Why would I be so happy? Why is this a happy thing? I could have had something more wild. I don't. I'm happy I don't. Why am I so happy? Let's see. 3 out. Over the disk. Is this ringing a bell?
Oh, yeah.
Yeah, it's r squared if I do this in polar. So, and if I do this in polar, it's going to be r dr d theta. So life is not as hard as you believe. It can look like a harder problem, but it actually, in reality, is not. So I have 3 times. Now I have r squared, I have r cubed, dr d theta, r between, okay. R was between 0 and big R. Yes. Theta was between 0 and 2 pi. So, I want you, without me, to compute the answer and tell me what you got.
Just say it.
Yep.
3/2 pi r.
So how did you do that? You said r to the 4/4 coming from integration times a 2 pi coming from integration times a 3. Are you guys with everybody? Is everybody with me on this? Okay, so the simplified answer will be that, where big R is the radius of the disk.
How would we have solved that integral without switching to polar?
It would have been a killer. Let me write it down. Because you want to write it, of course. Okay, 3 integral x squared plus y squared dy dx, just to make my life a little bit funnier, and then y between minus square root. You're looking for trouble, Alex. Okay, r squared minus x squared.
Yep.
2r squared minus x squared. And again, you could do what you just said, split into 4 integrals over 4 different domains, or do 2 up and down. And minus r and r, are you guys with? And then when you go and integrate, oh my God, you integrate with respect to y. He has nothing better to do than think what's going to happen on this. Well, he's right. So you can get x squared y plus y cubed over 3. Between those points, minus squared, and from that moment I will just leave it and go for a walk because I will not have the patience to do this. But, just a second, Matthew. For this kind of stuff, of course, I could put this in Maple. I could even, you know, Maple has these little interactive fields, like little squares, and you go and type there your endpoints, and even if it looks very ugly, Maple will spit the answer. If you know your syntax and do it right, even if you don't switch to polar coordinates, you put it in Cartesian, you give it the right data, it's going to spill the answer. Yes, ma'am?
I was out of the room. I was wondering why it's now y cubed and x cubed.
Because you integrate with respect to y first.
No, he's asking why
For the
arrows
original,
switch.
so when I walked out, it was negative y.
Y put
See,
minus?
It's
If I didn't
Okay.
put
It's a new problem,
minus,
that's what he's confused about.
Yeah, because I was...
He walked out of the room during the previous problem and came back during this one, and now he's confused.
you don't care about what Alex asked.
Oh, No.
You don't get, okay, you see, okay.
I like the polar coordinates.
Okay, let me ask you a question before we talk any further. I was about to put a plus here. What would have been the problem if I had put a plus here? If I worked this out, I would have gotten x squared minus y squared. Would that have been the end of the world? No, but it would have complicated my life a little bit more. Let's do that one as well.
Yeah, I was just curious on how you do one of these problems when you can't switch to polar.
Right, let's
And
see
that's why I
what,
asked.
because actually even in this case, life is not so hard, not as hard as you think. The persistence in mathematics. You never give up on a problem that freaks you out. That's the definition of a mathematician. 3x squared minus 3y squared over the dx dy. Do it slowly because I'm not in a hurry. We are almost done with 13.4 and I'm not in a hurry. I'm going to erase. This is okay, right? It was just the minus sign that gave.
Well, not the minus sign. I was just wondering because in the previous problem we were doing the ellipse. We started out with the equation with the
Yeah, but
negative y.
for
x
this
prime.
one, that's
Yes.
just a lemma
Okay.
that says this is the double integral of, this is the area of the domain D. It's just a consequence, a corollary if you want. It's a consequence of Green's theorem.
Okay.
And we forgot that consequence of Green's theorem and we say goodbye to that. But while you were out, this is Green's theorem, the real Green's theorem, the one that was on my t-shirt. I mean, there are several Green's identities, but the famous Green theorem is the one that says when you have, this is what we apply here, integral of m dx plus m dy, you have double integral of m sub x minus m sub y dx dt. Over C, over D. So assuming we would have had this case of maybe me not paying attention or being mean and not wanting to give you a simple problem, and what do you do in such a case? It's not obvious to everybody, but you will see it's so pretty at some point if you know how to get out of the mess. Alex was already thinking, but I'm using polar coordinates, so that's our cosine that I have to go back to the basics. If I go back to the basics, ideas come to me, right?
Yeah.
So, there, okay. R, let's put the R, the theta first just to get rid of it because it goes on my nerves. This is 0 to 2 pi. This is 0 to R. And now you say, okay, in our mind, because we're lazy people, plug in those and pull out what you can. A 3 out equals for what? Inside you have R squared. Do you agree? Okay. And times your favorite expression, which is, I need to leave more room. Your favorite expression, which is cosine squared theta minus sine squared theta. And you're going to ask me why. You shouldn't ask me why. You just square these and subtract them and see what in the world you're going to get. Because you get R squared times cosine, well, cosine squared minus sine squared. I'm too lazy to write down the argument. But you know enough trigonometry. Yes, do you see why it's important for you to learn trigonometry when you're little? Little. You may be 15, 16 in high school, or you may be freshman year. I don't care when, but you have to learn that this is the cosine of the double angle.
Yep.
How many of you remember that? Maybe you learned that. Remember that? Okay. I don't blame you at all when you don't remember, because since I've been the main checker of finals for the past 5 years, it's a lot of finals.
It's got an ER there as well.
Yeah, the R is there. That's exactly what I wanted to tell you, that why I left some room. This theta could be T. The double angle formula did not appear on many finds. And I was thinking it's a pity, and when I asked the instructors in general, they say, well, students have trouble remembering or understanding it. This later on, by avoiding the issue, you sort of bump into it for the first time in Calc 2, because in Calc 2 there are many trigonometric formulas, and then you bump again inside it in Calc 3, and it never leaves you. So this, just knowing this is going to help you solve the integral. Let me put the R nicely here. And now finally we know how to solve it, because I'm going to go ahead and erase it. All right, so what is good for us is that, as Matthew observed a month ago, whenever you have a product of a function in R only and a function in theta only, your life becomes easier because you can separate the two integrals in two different products. So that's Fubini's theorem, and you have 3 times the part that depends only on R and the part that depends only on theta. Let's put them separately. The theta and the R. And what do you integrate when you integrate? R cubed. Attention to that, R cubed. From 0 to R. Okay?
And there will be cosine theta.
And then you have 0 to 2 pi cosine 2 theta. Now, let me tell you what, okay? Because when I was young, I was naive, and I always started with that. You should always start with the trig part in theta, because that becomes 0. So no matter how ugly this is, I've had professors who were playing games with us, and they were giving us some extremely ugly thing that would take forever for you to integrate, or sometimes it would have been impossible to integrate. But then the whole thing would have been 0, because when we integrate cosine 2 theta equals sine 2 theta, sine 2 theta and 2 pi and 0 are the same thing. 0 minus 0 equals 0. So the answer is 0. I cannot tell you how many professors I've had who played this game with us and gave us something that discouraged us. No, this is piece of cake compared to what I have. Some integral that would go over 2 lines with a huge polynomial here, something. But in the end, the integral was 0 for such a result. Yes, sir.
So question,
Yeah.
could we take that force and prove that it was conservative?
So that now I'm questioning this. I'm not questioning you, but is the force that is with you conservative? What is the original force that Alex is talking about? If I take y cubed I plus x cubed j, and you have to be very careful, is this conservative? Really?
Well, is it like the
Why
other
would
one?
it be
There's like,
conservative?
y squared plus x squared over 2 is kind of like that. Because when you
Why is it not conservative?
Does it pass the sector?
It doesn't pass the curl test, it doesn't pass the, so M, let's call it P and Q. P sub y is not equal to Q sub x. If you prime this with respect to y, you get 3y squared. If you prime this with respect to x, you get 3x squared. So it's not conservative, and still I'm getting, it's a loop, and I'm getting a 0, sort of like I would expect if I had independence of path. What is the secret here?
That is conservative given a condition.
Yes, given a condition that your x
This
and y
fits
are
the-
moving on a certain circle. That the magic thing happens because this is a symmetric expression, and x and y are moving on a circle, and one is the cosine theta and one is sine theta. So in the end, it simplifies out. It's really beautiful. But in general, if I would if I would have this kind of problem, and if somebody asks you, is this conservative, the answer is no.
Yeah.
Let me give you a few more examples. One example that maybe will look hard to most people. Consider I'm sorry, guys. The vector value function given by f of xy in plane R2 value. No, I mean defined in R2 with values in R. Okay, what am I saying? Typical, but typical exam problem. And I saw it in Texas A&M as well. So maybe some people like this kind of ABCD type of problem. Is f conservative?
6, 6.
Prove. Your
6xy.
plane.
Yep.
You already did. Good
Yeah.
for you guys. So if I gave you one that has 3 components, what would you have to do again? Curl. Compute the curl. You can, of course, compute the curl also on this one and have 0 for the third component, but the simplest thing is to do F1 and F2. F1 prime with respect to y equals F2 prime with respect to x. So I'm going to make a smile here. You realize that the authors of such a problem, whether they are Tech or Texas A&M, they do that on purpose so that you can use this result to the next level, take it to the next level, and then say compute the path integral over the curve
Whatever nasty
x
curve you want.
cubed, yeah, x cubed y cubed equals 8 on a path that connects points 2, 1 and 1, 2 in plane. And does this integral depend on path? Stay y. And you see, they don't tell you find the scalar potential, which is bad. And many of you will be able to see it because you have good mathematical intuition and a good computer process running at the background of all the other processes. We are very visual people. I don't know if you realize, but every time we just stare at each other through the classroom, there are hundreds of distractions. There is the screen, there is somebody next to you who's sneezing, all sorts of distractions. Still, your computer, your unit can still function trying to integrate and find the scalar potential, which is a miracle. I don't know how we managed to do that after all. If you don't manage to do that, what do you have to set up? You have to say, find, is there, well, you know there is. So you're not going to ask, not going to question the existence of the scalar potential. You know it exists, but you don't know what it is. What is f such that f sub x will be 6xy plus 1, and f sub y will be 3x squared? And normally you would have to integrate backwards. Now, I give you 10 seconds. If in 10 seconds you don't find me a scalar potential, I'm going to make you integrate backwards, solve this system, and find the scalar potential by integration. The way you should, if you weren't very smart. But I think you're smart enough to smell the potential. Very good. But what if you don't? Okay, I'm asking. So we had 1 or 2 students who figured it out. Why if you don't? What if you don't? If you don't, you can still do perfectly fine on this problem. Let's see how we do it without seeing, guessing, or not guessing. His brain was running in the background. He came up with the answer. He's happy. He can move on to the next level. But,
You can integrate both sides with respect to their...
right, and then match them.
Make them work.
Make them work. So, integrate with respect to x, 6xy plus 1. I'm sorry, guys. And what you get, you're going to get
3x squared y
3x squared y plus x.
plus c.
And plus a c of y. And then take this fellow and prime it with respect to y, and you're going to get, it's not hard at all, you're going to get 3x squared plus nothing, plus c prime of y, and it was good because God gave you a simple one. So sometimes you can have something here, but in this case it was just a 0, so c is kappa, is a constant. So instead of what Nitish found, I could have put a plus kappa here and it still does work. So on such a problem, I don't know, but I think I would give equal weight to ABC. Compute the path integral over the curve. This is it looks horrible as an inclusive curve, but I know there is a path that connects the points 2, 1, and 1, 2. All I had to pay attention in my mind is that these points actually are on the curve, and they are because I have 8 times 1 equals 8, 1 times 8 equals 8. So while I was writing, I had to think a little bit about that. If you were to draw, well, that's for you to find out when you go home. What do you think this is going to be? Actually, we have to do it now because it's a lot simpler than you think it is. X and Y will be positive. I can also restrict that, but it looks horrible, but it's actually much easier than you think. So how do I compute that path integral that connects the points? I'm going to have the fundamental theorem, which says f little f at q minus little f at p, which says that little f is 3x squared y plus x at 2, 1 minus 3x squared y plus x at 1, 2. So all I have to do is go ahead and, do you see what I'm actually doing? It's funny. This is, which one is the origin and which one is the endpoint? The problem doesn't tell you. It tells you only you are connecting the 2 points. But which one is the alpha and which one is the omega? Where do you start? You start here and here, or you start here and end here? Okay, sort of arbitrary. How do you handle this problem? Depending on the direction, pick one. Direction you move on along the arc, it's up to you. And then you get an answer, and if you change the direction, what's gonna happen to the integral?
There's a right side.
It's gonna just change the sign, and that's all. So you have 3 times 4 times 1 plus 2. Guys, keep an eye on my algebra, please, because I don't want to mess up. Am I right here?
Yes.
So how much? 14, is it?
Minus 7.
Minus 7, minus 6, minus 7, you're right. You see how to do 7. Good. Wonderful. So we know what we get, and we know this does not depend on the path. How much blah, blah, blah does the instructor expect for you to get full credit on the problem?
Just enough to explain.
Just not to explain, about 2 lines, 1 line, 2 lines, no more. Saying, you can say it in many ways. You can say, this is the theorem that shows independence of path integral. If the force F vector value function is conservative, then this is what you have to write. This doesn't depend on the path C, and you apply the fundamental theorem of path integrals for the scalar potential, and that scalar potential depends only on the endpoints that you're taking. And the value of the work depends only on the scalar potential and the 2 points. That's enough. That's more than enough. What if somebody is not good with wording and says, I'm not gonna write her all that explanation. I'm just gonna say whatever. I'm gonna give her the theorem in mathematical compressed way, and I don't care if she understands it or not or something. Even if you write this formula with not much wording, I still give you credit for this part. But I would prefer that you give me some sort of explanation. Yes, sir.
If you said answer was 0, then only it would have been path independent. The answer would have been 0 then instead of 7.
No, the answer would have been for sure 0 if it was along a loop, right? If it were along a closed curve that where it ends, where it starts, it ends. Even if I take a wiggly road between the 2 points, I still get 7, right? That's the whole idea. Am I clear about that? Are we clear about that? Let me ask you though, how do you find out? Because I don't know how many of you figured out what kind of curve that is, and it looks like an enemy to you, but there is a catch. It's an old friend of yours, and you don't see it. And so, what is the curve? What is the curve, and what is this arc of a curve between 2, 1 and 1, 2? Can we find out what that is? Of course, it looks like, oh, cubic. It's a fake cubic. It's a fake cubic.
Two functions together?
That's just y equals 2x.
Let's see what this is. xy cubed minus 2 cubed equals 0. We were in 4th grade when, well, our teachers, what did our teachers teach us when we were little? That this, if you divide it by a minus b, I wasn't little, I was in high school, well, 14-year-old.
A cubed.
A squared
A squared.
minus 2ab.
No,
Plus 2ab.
very good. Plus AB, not 2AB.
Oh, darn.
Plus B squared. Okay, I suppose you don't believe. Let's prove this. Let's multiply a cubed plus a squared b plus ab squared. I'm done with the first multiplication. Minus ba squared minus ab squared minus b cubed. Do they cancel out? Yes. Good. Cancel out and cancel out. Thank God, we proved it. We proved it. Why? Because maybe some of you, nobody gave it to prove before. So as an application, what is this? There's who is A and who is B. A is xy, B is 2. So you have xy minus 2 times all this fluffy guy, xy squared plus 2xy plus 4. And I also said, because I was sneaky, that's why to make your life easier or harder, xy is positive. When I said xy is positive, what was I intending? I was intending for you to see that this cannot be 0 ever. So the only possibility for you to have 0 here is when xy equals 2. And xy equals 2 is a much simpler curve. And I want to know if you realize that this will have the points 2, 1 and 1, 2 staring at you. Have a nice day today. Take care. And good luck. What is it? Some sort of animal. It's a curvilinear curve. It's not a line. What is it? Talking about conics, because I was talking a little bit with Casey about conics. What kind? Is this a conic? Yeah. What is a conic? A conic is any kind of curve that looks like this in general form. Oh my God. A, B, C, D. Now I got my ABC. Plus F equals 0. This is a conic in plane. My conic has missing everything else. And B is 0. And there is a way even to show, I showed you how you know what kind of conic it is. A, B, B, C. A is positive, is 0. No, A is 0, B is, it should be 2 here. So you split this in half, 1 half, 1 half, and 0. The determinant of this is negative. That is sort of discriminant, the way we call it, discriminant of the conic. So it cannot be an ellipse. So what the heck is it? Well, I'm silly. I should have pulled out for y. And I knew that it goes down like a 1 over x. But I'm asking you, what in the world is that as a conic? Because you say, wait a minute. I know this curve since I was 5-year-old in kindergarten, and this is the point 21. It's on it, and there is a symmetric point for your pleasure here. 1, 2. And between the 2 points, there is just one arc of a circle, one arc of a curve, and this is the path that you are dragging some object with force F. I don't know. You are computing the work of maybe you're computing the work of a neutron between those 2 locations. It's a hyperbola. Why, Nitish? Yes, sir.
I was just wondering, could we have gone to x, y equals 2?
Yeah, way quicker.
X cubed, y cubed equals 2 cubed. Then you just do both sides.
That's what I did.
Cube root.
Didn't I do that? No, because in general it's not, you cannot say if and only if xy equals 2 in general. You have to write, to decompose the polynomial. You were lucky,
Well, we
this
could
was
have divided
positive.
by x cubed. We could have just divided everything by x cubed and then taken the cube root of both sides.
He's saying the same thing, but in mathematics, we
I mean, it
don't,
wouldn't
let me
be-
show you something.
So it
Yes,
would
sir.
work for this case, but not necessarily for all cases.
Yeah, let me show you some other example where you just, how do you solve this equation? By the way, the math field test is coming, only if you're a math major, sorry, junior or senior. In one math field test, you don't have to take it. But some people who go to graduate school, if they take the math field test, that sort of replaces the GRE, if the school agrees. So there was this question, how many roots does it have and what kind of roots they are? And 2 are imaginary and 1 is real.
Yeah.
But everybody said it only had 1 root. And how can it have 1 root if it's a cubic equation? So 1 root, x1 is 1, the other 2 are imaginary.
-1.
This is the case in this also. You have some imaginary roots. So those roots are funny, but you would have to solve this equation because this is x minus 1 times x squared plus x plus 1. So the roots are minus 1 plus minus square root of b squared minus 4ac over 2, which are minus 1 plus minus square root of 3I over 2. Do you guys know these, how they are called? You know them because in some countries we learn them, but you know the notations?
What they call them?
Yeah. That is a Greek letter in India probably. In my country it was omega, but I don't think
What do you call it?
iota.
Iota.
But we call them omega and omega squared because one is the square of the other. They are of course both imaginary, and we call this the cubic roots of unity. And of course this is not, you say, Magdalena, why would you talk about imaginary numbers when everything is real? Okay, it's real for the time being while you are still with me. At the moment you're gonna say goodbye to me and enroll in 3350, your life is gonna change. In that course, they will ask you to solve this equation, just like we asked all our 3350 students. To our surprise, the students don't know what imaginary roots are. Many, you know, you will refresh your memory. But the majority of the students didn't know how to get to those imaginary roots. You're gonna need to not only use them, but also express these in terms of trigonometry. So, just out of curiosity, since I'm already talking to you, and since I'm preparing you a little bit for the differential equations class, where you have lots of electric circuits and applications of trigonometry, these imaginary numbers can also be put, they are in general of the form a plus ib, a plus minus ib, and we agree that in 3350 you have to do that. Out of curiosity, is there anybody who knows the trigonometric form of these complex numbers?
Isn't it R e to the j?
So you would have exactly what he says here. You see, this number will be, if it's plus, whatever, R e to the I theta. He knows a little bit more than most students.
Oh, that's,
And that is cosine theta plus I sine theta. Can you find me the angle theta if I were to write cosine theta plus I sine theta? Or cosine theta minus I sine theta? Can you find me the angle theta? Is it hard? Is it easy? What in the world is it? Think like this. Think like, oh, we are done with this example, but I'm just saying some things that will help you in 3350. If you want cosine theta to be minus a half, and you want sine theta to be root 3 over 2, which quadrant, which, 4 quadrants there are, right? Which quadrant are you in? The second quadrant. Very good. Alrighty, so think cosine, okay. If cosine would be a half and sine would be root 3 over 2, you would be in first quadrant, and what angle would that be?
That's a
60 degrees, which is pi over 3, right?
Mhm.
But you're not at pi over 3 is your friend. Look, he's happy. Well, he's there somewhere. Where you are here, you are at what?
120.
When how much is 120? Very good. How much is 120 in pi?
4 pi.
No.
2 pi over 3.
2 pi over 3. Excellent. So 2 pi over 3, that would be, if you were to think about it, this is in radians. Let me write radians. In degrees, that's 120 degrees, right? So to conclude my detour to introduction to study 350, when they will ask you to solve this equation, x cubed minus 1, you have to tell them like that. They will ask you to put it in trigonometric form. x1 is 1, x2 is cosine of 2 pi over 3 plus I sine 2 pi over 3, and the other one is x3 equals cosine of 2 pi over 3 minus I sine of 2 pi over 3. And last thing, because I should let you go, there was no break. I squeezed your brains really bad today. We still have like 15 minutes. I stole from you. No, I stole really big, because we would have, yeah, we still have 15 minutes, but the break was 10 minutes, so I didn't give you a break. What would this be if you wanted to express it in terms of another angle? That's the last thing I'm asking.
3 if you for
Not
cosine.
minus, like cosine of an angle plus I sine of an angle. You would need to go to another quadrant, right? And which quadrant?
Or
You said it before, that would be 4 pi over 3.
Yeah.
And 4 pi over 3. Keep in mind these things with imaginary numbers, because in 3350 they will rely on you knowing these things. And
Then he applied Euler's formula out there.
hmm?
Then he applied Euler's formula out there.
Oh yeah, this
Get
is,
that.
by the way, this is called Euler's formula.
basically in middle school they teach you and they tell you when the discriminant is small, then there's no solutions.
Yeah,
And
when
you
the
go to factorial.
discriminant is less than 0, there are no real solutions, but you have in
Uh,
pairs imaginary solutions. They
Yeah.
always come in pairs. Do you want me to show you probably the most important problem in 3350 in 2 minutes, and then I let you go?
Sure.
Okay. So, somebody gives you the equation of the harmonic oscillator. And you say, what the heck is that? You have a little spring, and you pull that spring, and it's gonna come back. You displace it, it comes back, and it oscillates back and forth, oscillates back and forth. If you were to write the solutions of the harmonic oscillator in electric circuits, there would be oscillating functions, so it has to do with sine and cosine, so they must be trig. If somebody gives you this equation, let's say a x squared, y double prime of x plus minus b plus equals 0. And here's a y. Why would that show up like that? Well, Hooke's law tells you that there is a force. And there is a force, and the force is mass times acceleration, and acceleration is like this type of second derivative of the displacement. And F and the displacement are proportional. When you write F equals displacement, let's call it y of x. When you have y of x, x is time, that's the displacement, that's the force, that's the k. So you have a certain Hooke's constant, Hooke's law constant.
Yep.
So when you write this Hooke's law, it's going to become like that. Mass times y double prime of x equals, this is the force, k times y of x. Right? But it depends, because you can have plus minus. All right? So you can have plus or minus, and these are positive functions. And you have two equations in that case. One equation is the form y double prime plus, give me a number, cy equals 0, and the other one will be y double prime minus cy equals 0. Okay? All right. Now, how hard is to guess your solutions? Can you guess the solutions with naked eyes, or?
Well, e to the x has to be one of them.
So if you have e to the something, if you didn't have a c, it will make your life easier. Forget about the c. The c will act the same again. So here, what are the possible solutions? E to the t is one of them. E to the x is one of them, right? So in the end, to solve such a problem, they teach you the method. You take the equation, and for that you associate the so-called characteristic equation. For power 2, you put r squared. Then you minus, and for, this is how many times is it primed? No times, 0 times. So you put a 1. If it's primed 1 times, y prime is missing. If it's primed 1 time, you would put minus r, or whatever, equals 0. And then you look at the two roots of that. And what are they? Plus minus 1. So r1 is 1, r2 is 2. And there is a theorem that says
R2 is minus 1.
R2 is minus 1, x1, excuse me. If what, okay, there is a theorem that says all the solutions of this equation come as linear combinations of e to the r1 t and e to the r2 t. So linear combination means you can take any number a and any number b here, or a c1 and a c2, anything like that. So all the solutions of this will look like e to the t with an a in front plus e to the minus t with a b in front. Could you have seen that with naked eye? Well, yeah. I mean, you were smart and you guessed 1, and you said e to the t satisfied, because if you put e to the t and prime it as many times as you want, you still get e to the t. So you get 0. But nobody thought of, or maybe some people thought about e to the minus t.
Yeah, I was about to go through that one.
You were about.
You just asked for a solution.
So even if you take e to the minus t, you get the same answer, and you get this thing. All right, all the combinations will satisfy the same equation as well. This is a superposition principle. With this, it was easy, but this is the so-called harmonic oscillator equation. So either you have it simplified, y double prime plus y equals 0, or you have some constant c. Well, what do you do in that case? Let's assume you have 1 here. Who can guess 2 solutions?
0 equals sine.
No, 0 is the trivial solution and it's not going to count. You can get it from the combination, from the trivial combination.
Y equals sine t and
Sine t is a solution because sine t prime is cosine. When you prime it again, it's minus sine. When you add sine and minus sine, you get 0. So you just guessed 1 and you're right. With a face. Do you see another one? Cosine t. They are independent, linearly independent, and so the multitude of solutions for that, I taught you like a whole chapter in 3350. Now you don't have to take it anymore. It's going to be a cosine t
E to the IT.
plus b sine t. I'll tell you in a second. All right, it has to do with e to the it in a way. Okay, so you guessed that all the solutions will be combinations like on a monitor when you have cosine and sine. If you add them up, when multiply and add them up, you get something like the monitor thing at the hospital. So any kind of oscillation like that is a combination of this kind. Maybe with some different like phases and amplitudes. You have cosine of 70 or cosine of 5t or something. Let me show you what they are going to show you in for the harmonic oscillator equation, how the method goes. you solve the characteristic equation. So you have r squared plus 1 equals 0. And here's where most of the students in 3350 fail. Now when they understand that, and some of them say, okay, this has no solutions. Some of them even say this has solutions plus minus 1. I mean, crazy stuff. Now, what are the solutions of that? Because the theory in this case says if your solutions are imaginary, then y1 will be e to the ax cosine bx, and y2 will be e to the ax sine bx, where your imaginary solutions are a plus minus id. It has a lot to do with that Euler's formula in a way. So, if you knew the theory in 3350 and not be just very smart and get these by yourselves by guessing them, how were you supposed to know that? Well, r squared equals minus 1, right? The square root of minus 1 is I. Or negative I. So R1 is 0 plus minus I. So who is A? A is 0. Who is B? B is 1. So the solutions are e to the 0x cosine 1x and e to the 0x sine 1x, which is cosine x sine x. Now you know why you can do everything formalized and you get all these solutions from a method. This method is an entire chapter. It's so much easier, 3350 is so much easier than Calculus 3. You will say this is easy, it's a pleasure. You spend about 1/4 of the semester on this method. So now you don't have to take it anymore. You can learn it all by yourself and you're gonna be fine. We'll be ready for the next thing. So I'm just giving you courage. If you do really, really well in Calc 3, 3350 will be a breeze. You can breeze through that. You only have the probability and stats for most engineers to take. Math is not so complicated.